Hello. So I'm going to try to explain why the Diffie-Hellman protocol is both very simple and very efficient as an encryption protocol. So we always have to assume a certain mathematical context, and our context has to be a group whose cardinality, a cyclic group whose cardinality is a prime number. We're going to take 11 here, and we're not going to get into the details of why it has to be a cyclic group like that. And we need also what we call a generator, alpha, and we're going to set it up to number 2. So these are our initial parameters. So what does it mean that our group, cyclic group of cardinality 11, that means that every computation we're going to make are going to be made modulo 11. And so how does the modulo function works? Well, 1 modulo 11 equals 1, 2 modulo 11 equals 2, etc., etc. But if you go to 11 modulo, sorry for my handwriting, equals 1, it's actually equal to 0. You go back to 0, just like the time goes back to 0 at midnight, right? And then naturally 12 modulo 11 equal 1, etc., right? So it keeps going, right? 100 modulo 11 equals 1. Why? Because 9 times 11 equals 99 plus 1, 100. So it's really the remainder if you want. So that's the modulo operation. And here we are considering ourselves in a world where nothing can go beyond 11. And that's a very important concept for encryption. So we considered, we're going to try to see, so why is number 2 a generator? And here is how it works. We're going to consider a certain function for all these numbers from 1 to 10. And I take 1 to 10 because I just keep the 0 and the 11. And I'm not going to go into details of why here. We're gonna call this function f. And here is the function. I take alpha, here it's the number 2, to the power of x, and I try x all the numbers that are in my group except 0 and 11. Alpha to the power of x modulo 11, right? I mean modulo p if I use the parameter, but this is nothing else than 2 to the power of x modulo 11, right? So I'm going to compute this for all of this. It's actually very easy to compute, right? 2 to the power of 1 is 2. 2 modulo 11, of course, is 2. And then 2 to the power of 2 is 4. So 4 modulo 11, it's still 4. And then 8 modulo 11 is 8. But now if I do 8 times 2, 16. 2 to the power of 4 equals 16. 16 modulo 11 is 5, right? So it doesn't go beyond 11, right? Of course. And then 16, 32. 32 modulo 11 is 10, because 22 is 2 times 11, so 32 minus 22 equals 10. But now another way to do it is actually something really interesting with the modulo operation. It has to do with why Diffie-Hellman is so interesting and powerful. You can actually just, instead of doing like 32 modulo 11, you can just take the last number 5 and multiply by 2, and you get 10. 10 modulo 11 is 10. It's easier to compute and it works. It's always the same. Like you can do the same thing here. 2 times 10 is 20. 20 modulo 11, 9. 2 times 9, 18. 18 modulo 11, it's 7, etc. So it's actually a fairly easy thing to compute, right? It's easy mainly because this is a small number. And so 2 is a generator because basically from 1 to 10, I get all the numbers from 1 to 10 just associated with something that looks random with the initial numbers on different places, except the 7 that is at the same place. But so you have here all the numbers from 1 to 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? They're all here. So now, this little table is really all I need to understand the Diffie-Hellman protocol. And so we use here our little function, right, to go from x to f of x, this function we talked about. And the reason Diffie-Hellman is efficient and works is because of two main points. There's two reasons why it works. First, because f, this function, is a one-way function, at least computationally. So that's the first reason, a one-way function. And second reason is because there is a specific combination. If we consider two arguments, x1 and x2, to which are associated f of x1 and f of x2, there is a special combination of x1 crossed with f of x2, okay, these two, that is related or equivalent to x2 crossed with f of x1. Okay, so these two. So basically, given that these are the private keys and these are the public keys, you basically have a special combination of a private key, my private key with your public key is going to be equal to your private key with my public key. So we can exchange here information, and while these are going to be try to use some color here. These are the public information. These two together cannot are not equal to this, right? But this is the shared key. This is a shared key. To get a shared key, you need to combine one argument with one value, right? If you consider that this is what we call argument, and this is the value. Yeah, you combine one argument with one value to get something equal to the other argument with the with the other combination argument and value. Sorry, I'm not making myself super clear, but we're going to take an example. It's going to make it much clearer. This is more like, in theory, here are the two ideas that make it so powerful and efficient. But now let's look at an example. Well, let's say that we have Alice and Bob, and Alice is taking number 4 as a private key, and Bob in blue is taking number 9. Okay, so then of course 4 and 9 are not shared, right? Alice and Bob are not going to share. Alice picked number 4 and Bob picked number 9. They are not sharing. These are their private keys, right? What they're sharing is the value of f of x, okay, 5 and 6, right? So Alice is sending 5 to Bob, and Bob is sending 6 to Alex. The first thing that is very, very important is that, and it makes it very powerful, is that f is computationally a one-way function. What does it mean? It means that if I give you 4, you can easily find 5, right? We just computed that together. If I give you 9, you can easily compute 6. That's actually what Alice and Bob are going to do each on their own side. They're going to have to compute the value of this function, right? But what is very interesting is that if I give you 5, it's actually really, really, really hard to find 4. And if I give you a 6, it's really, really hard to find 9. Why is that so? Well, we're not going to get into the details of that, but you can get a sense of, with the number 6, all you know is that 6 is the remainder of a power of 2. There is no like actual like computation that allows you to guess which power of 2 gives you 6, unless going through a brute force test of all of these, right? You start with 1, 2, 3. So you do exactly what we did, and then you arrive at 9. And you're like, oh, okay, yeah. If I do 2 to the power of 9, I get 6. So yeah, so 9 is the number corresponding to 6. Well, you can do it with 11 numbers, but this is not. This is too small, right? It's only for the example. If you start using 47, right, or 119, much higher prime numbers, this is going to be at a certain level just impossible to compute, completely impossible, like physically impossible in a reasonable time. So so that's the first very important feature, is that it's really hard to go back. Again, the intuitive idea is that you're just given a remainder, right? So this number 6 doesn't have much to do with 9 in itself, right? 6 has much more to do with 2 and 11 than it has to do with 9. So it's hard to explain, but I think you can get the intuition of how you know. How do you get 6? Well, we do 2 to the power of 9, and 2 to the power of 9 is equal to a certain number of time going through 11, right? A lot of time. You're gonna go to from 1 to 11, a very, very large number of time, and at some point, assuming it's kind of like a clock, and this is, this is 0 and 11, and this is like 5, 6, you go through it certain number of time, and at some point you're going to go one more time when you're at the end, just until the number 6, and you're going to stop there because it's going to be equal to 2 to the power of 9. Well, this number 6 doesn't tell you much about the number 9, right? I mean, it's very hard to retrieve. It's easy to find the number 6 because you have this kind of process, but going backward is actually very hard. So anyway, that's the one-way function argument, and that's a very important piece. So and the second piece is that if I combine your 6, as we said, if I combine your 6 and my 4, I can get something that is equal to combining my 5 and your 9, right? And here is the operation. So basically the combination is this one, right? If I combine my 5 and your 9 together, it's equal to a certain combination of my 4 and your 6. And here is the combination is I compute the public key to the power of the private key, right? So 5 to the power of 9, always modulo 11, right? Always, that's the world we live in, we always do modulo 11. And if I compute same thing the other way, 6 to the power of 4, that's actually the other way, I'm sorry. 6 to the power of 4 is here because I have your 6, that's a public key I receive, and I have my own private key. 6 to the power of 4 modulo 11, and here 5 to the power of 9 modulo 11. These are both equal to 9. I mean, this you can compute with the calculator. It's not too hard. You do what you do is that you do 6 to the power 4 divided by 11, and you take the number before the comma, okay, and then you take this number x and then you do 6 to the power of 4 minus 11 times x, right? And it's going to give you 9. I don't remember the exact value of x, but the result is 9. So this gives you exactly the same key, right? And again, this is a small key because we took a small example, but it can be a much larger number when you take a p equal to 47, 119 or something like that. So that's the second feature, right? That's the second feature that allows us to find exactly the same number here using only my private key and your public key, right? I don't need Alice doesn't need the 9 from Bob, and Bob doesn't need the 4 from Alice. Only what is shared public key, and you cannot retrieve this number using only what is shared. If you try to take only the public information, 5 and 6, you will never find 9, right? And as a matter of fact, if I try to compute 5 to the power of 6 modulo 11, it's equal to 5, and 6 to the power of 5 modulo 11 is equal to 10, right? So both of these, they don't work, right? They are not equal to the 9, the shared key. So this is the shared key. And so the public information is not enough. Now you could say, well, yeah, I know it's not enough, but I know that 5 has been computed from 4 and 6 has been computed from 9. So what is that? If I inverse the function and try to retrieve 4 or retrieve 9 from the public information that is shared and that I can listen, with the intention to decrypt the message, the key. And you cannot do that because of the first feature we talked about, because it's a one-way function, right? Because figuring 9 from the number 6 or figuring 4 from the number 5 is computationally very hard. It is not very hard in our small example again, but in general, it's very hard. We can't do that. So that's my very humble attempt to try to explain why this protocol is so powerful. I hope it helps a little bit. But again, it's really the combination of, if I had to recapitulate, the fact that this specific function, alpha to the power of x modulo p, is a one-way function computationally, okay? And the fact that when you have two players, two private key, x1 and x2, the argument, a certain combination described here of the argument of one and the value of the other one is equal to the combination of the argument of the other one and the value of one. Okay, so thank you very much for your patience listening to all that, and let me know if you have questions or comments. Thank you.